Oh, yeah, I guess we could have. I was having so much fun back up here. Okay. I wanted to go through that.
Oh,
I wanted to go through that process just to refresh your memory on
Okay.
the fact that you got a product of time-dependent functions. It would have been much simpler to go here.
well, that's what I was thinking at first.
And
but
check it
it's-
out, differentiating with respect to time here, pretty nice. X double dot is equal to
Y dot.
Y dot,
Which is 3.
which is 3. Okay? That was much less exciting. This is much more fun. Okay. Okay, now, what about the acceleration? Remember, we're not looking for just x double dot, we're looking for the acceleration. So here we are on our path. I didn't plan on taking this much time on this. This thing's telling us that this thing, x double dot, is this constant 3 inches per second squared. And what I want to point out to you is notice no matter where this is on the path, at least from this piece of information, you have two components of acceleration. One component that's tangent to the path and the other component that is normal to the path, giving you, here's your total acceleration right there. We actually are done. X double dot is 3. Y double dot we know was 0 and remains 0. And so the acceleration is indeed 3 inches per second squared remaining constant. So therefore, the acceleration equals 3 inches per second squared. And notice that it has an inward component. That normal acceleration component is inward, and it's got a tangential component. And as this moves further and further over on this square root function graph, and that thing remains 3, notice how the tangential component grows and the normal component will diminish. The tangential component will continue to grow, and in the limit, as this thing arcs over, the tangential component approaches 3 in a limit as this thing gets closer and closer to horizontal, and the vertical, or the normal component, heads towards 0. You with me on that? Make sense? Okay. Now, what I want to point out to you is something from yesterday. The normal component of acceleration is v squared over rho, and we know that as this arc continues to get flatter and flatter and flatter, that the radius of curvature gets longer and longer and longer, doesn't it? The further out there you go. And that's going to drive up this value. Now, of course, there's a trade-off going on because that speed is also growing. Okay. So anyway, that should give you cement some of this thinking for you a little bit. Let's move on to a different kind of problem. Okay? Point out on the same page, here's the kind of mechanism, and this is actually assigned to you. Here's a mechanism that's got some stuff going on. And if you want to jot the answer down, I happen to have written it here in the book, 2.24 millimeters per second on the speed, and the acceleration is about 2.06 millimeters per second squared.
I have a quick question.
Yeah,
Sometimes it seems in the book the only way to differentiate between units used in a problem is that they use SEC instead of S for seconds.
Yeah.
And that's something we just have to deal with. Okay.
Yeah, I usually write SEC down for seconds. My handwriting gets a little sloppy at times. All right. Let's go ahead and let's move over. How are we doing on time? We've got about 50 minutes left. Let's go over to the material on circular motion that I introduced to you yesterday in the last session. And let's look at a particular case, I'm sorry, of normal tangential. We introduced the normal tangential concept for speed or velocity and acceleration. And what I want to look at is the special case of circular motion, because there's lots of things in mechanical systems that are moving in circular motion. Okay. Okay, if you recall from the last session on this normal tangential material, that the velocity vector, do you have it in your head yet? Some of these fundamentals I'd like you to try to get them into your head. And what you can do if you have a hard time remembering, just think about something moving on a path. It's got a certain speed and happens to be in a tangential direction. So there's its magnitude and there's its direction. So you can refresh your memory pretty easily by just thinking about that. And then when you move on to the end of the realm of acceleration, going through that differentiation process we did yesterday on this vector equation, we ended up with a normal component of acceleration and a tangential component of acceleration. So that acceleration comes out to be a normal component of acceleration, scalar times its unit vector in the normal direction, and the tangential component in the tangential direction. And the normal, we oftentimes write it and remember it as v squared over rho from what we derived yesterday. The speed squared over the radius of curvature, points inward towards the center of curvature, and I'll just keep saying that until it's cemented into your brain, okay? And then the tangential acceleration term is the time rate of change of this speed, isn't it? It's with the blinders on. So this v, the speed there, is s dot ds dt, and so the time derivative of that speed, this is in other words the derivative of a magnitude. Derivative of a magnitude is going to be s double dot. That tangential component of acceleration. That, I believe, is the way you typically see it in the book. Let me take a quick peek here. They show it as v dot, which is also s double dot. They show that as well. What's the magnitude of that acceleration? What's the magnitude of this acceleration? You have two orthogonal components here. Square root of the sum of the squares of the legs, right? Right. So you want to remember that the magnitude then is going to be the square root of the normal component squared plus the tangential component squared. That's useful. Let's look at circular motion now. The special case of circular motion. Here's a particle in circular motion. It's got some speed. It's got some, what's its radius of curvature?
It's the radius of the circle.
It's the radius of the circle, isn't it? And that's going to remain constant for circular motion. So we're dealing with a special case of circular motion. So our normal acceleration component then is going to be the speed squared over r. And I want to back off to something that's actually a pre-calculus item. If you have, let's set up a horizontal axis here, and let's say we have a rotation angle theta to get to the radial direction, and then the speed is hooked on out there, happens to be orthogonal and remains orthogonal to the radius vector. If we would take something that's incircular, traveling on a circle, let me use capital R here. If I would bend that radius, if I was teaching a trig class, this is exactly the way I'd say it. If I took that radius on a circle and I bent it on the arc, it would go about this far. Wouldn't it? About that far. Pretty good drawing. That is 1 radian of rotation. So a radius could be thought of as equivalent to 1 radian of rotation. And how many of those radiuses are there as you move around the arc?
2 pi.
There's precisely 2 pi of them. 6.28 approximately. Okay? So we know that the arc is equal to r times theta, without me going through more explanation about why that's true. Everybody comfortable with why that's, or where that comes from? Okay. If you take the time derivative here and hold that radius constant, this is like, think about this as a distance. Radius, length per radian. Length per radian. So this is like, say, meters per radian times radian measure. And so that's the reason this turns out to be an arc length, is because that radius measured as in meters is equivalent to 1 radian of rotation. That's a conversion factor right there in this linear relationship. It's a conversion factor. Oftentimes you hear instructors say, oh, just make sure you use radian units and then ignore the radians. Well, that's not true. They're certainly there. Okay. So S dot then is equal to R theta dot. What's theta dot? Meters per radian, and this is the time rate of change of angle, radians per second is a real common unit we use. Okay? And you end up with meters per second for the speed on the arc. So this is equal to R theta dot. If we put R theta dot now into this expression for V, we have R squared theta dot squared over R, and we get something familiar from physics of R theta dot squared. So that's another way you oftentimes see normal acceleration expressed for circular motion. Notice it's a function of the radius, so larger radius, greater normal acceleration required. Also, a function of the square of the angular velocity. This theta dot is called the angular velocity. This is called the S dot is called the time rate of change of arc length, or more simply, linear velocity. Okay. So the linear velocity is a linear function of the angular velocity. And it's also linear, the linear velocity is also a linear function of the radius. So if you double the radius, you're going to double the velocity on the arc if the omega is constant. Excuse me, if the theta dot is constant. We're oftentimes called angular velocity omega. So if you have something in rotation, circular rotation, at a constant angular velocity, so many RPMs, revolutions per minute, at a constant, then as you move to a larger and larger radius, you're proportionally increasing the linear velocity on that arc, the speed at which the item on the curved arc is traveling as it moves around this. Okay? So there's the normal acceleration. Tangential acceleration comes from the rate of change of this right here by holding this speed, holding this r constant and taking the time derivative of this. So if we come up here and we take the time derivative of the speed, and then this is the time derivative of a scalar quantity, we're going to get v dot, which is s double dot, which is equal to, holding r constant, r theta double dot. And that is your tangential component of acceleration. Here's our normal acceleration term. Here's our tangential term. So for circular motion then, we have that the speed is equal to r theta dot, oftentimes written r omega, and we have that the acceleration has two components, and those are r theta dot squared for normal, and r theta double dot on the tangential. So the true acceleration vector then in circular motion, its normal component is going to be your r omega squared term, and your tangential term is going to be your r, oftentimes we call this alpha, r alpha term, to replace theta double dot. So here's a summary of the circular motion items. There are numerous problems in textbooks and in the real world that are the special case where we can use this normal tangential path-dependent coordinates and these relatively simplified equations here. Okay, I think we should probably work a problem out involving this coordinate system, and it may or may not be circular motion, so we'll find something here in the book. Julie?
I'm sorry, I missed what the little curly Q thing is called.
That guy?
Yeah.
Alpha.
Oh.
It's like a fish swimming to the left.
I've
Alpha.
seen alpha before.
Yeah, you've seen alpha a lot. Okay. Thermal coefficient of expansion in strength of materials. Okay. Okay, good. And omega, angular speed, alpha, angular acceleration. Okay. The book shows you these equations right here. The last form of the normal they show in the book, where you have the speed times theta dot, that's not used too often, but it certainly could be. You could use it occasionally in a problem. Okay, let's go to find a problem here in the book now. Here's a problem with a camshaft system, four-cylinder automobile engine. This is your timing belt. Connects a bunch of different things in your engine, internal combustion engine. And most of the cars now used to use chains, and you could drive a vehicle if it's well built for hundreds of thousands of miles, and trucks and things like that, and they'd work just fine. But nowadays these are flexible composite type of belts material, and you have to replace them periodically. I have two vehicles that need timing belt replacements. If this thing breaks, oftentimes it can put the camshaft, which drives the valves in the engine, out of sync with the pistons that are moving up and down, and that can cause real problems.
It pretty much shuts the truck down.
Yeah.
I've had one break on me.
You had? Yeah.
It sucks.
Yeah, there's a name for the type of engines. One of them, you can actually, the timing belt can break, and as long as you pull over relatively quickly, it's not going to hurt the engine, probably like your truck. But other times it can get, if it gets out of whack, there's a free spinning or something they call them, and it can just totally destroy your engine if you don't have
It
the
killed mine. It shut it down like that. As
Okay.
soon as I heard that, boing, dum, dum, dum.
Yeah, okay, and then you had to get a rebuilt, totally new rebuilt engine.
No.
Okay, well, back to the problem,
The
okay?
other truck I had.
Here's the drive system for a four-cylinder engine. And as the engine revs up, the belt speed, V, changes uniformly. So it's increasing from 3 meters per second to 6 meters per second over a 2-second interval. Calculate the magnitude of acceleration of points P1 and P2 halfway through this time interval. So P1 is located up on the edge of the camshaft sprocket on a radius of 60 millimeters there. And P2 is out here on the belt in its motion. And this was an even numbered problem. I happen to have written the answers down out of my solution manual. So our objective is to get to those answers.